we're going to practice making graphs of position, velocity, and acceleration. So let's take this example. You're on a bicycle, you start at rest, and you accelerate. You start moving faster and faster and faster until you get to your maximum speed of 10 meters per second. And it takes you 4 seconds to do that. And then you stop pedaling and you coast at that constant speed for the next few seconds. Why don't you graph that velocity versus time curve? So if we start out at rest at t equals 0, and 4 seconds later, 1, 2, 3, 4, we're at our maximum speed of 10 meters per second. And what does the curve look like between those 2 points? It looks like a straight line. Constant acceleration, the velocity changes by the same amount in each time interval. So it's linear. After 4 seconds, what does our curve look like? It looks like a horizontal line because our velocity doesn't change. It stays the same. It's 10 meters per second over this entire time interval. Well, you know what the next question is going to be, don't you? Now you're going to sketch the acceleration versus time curve that corresponds to this velocity versus time curve. We know that the acceleration is the time rate of change of the velocity function. So that means it's the slope of the velocity function. That's the instantaneous acceleration. At any instant in time, I could look at this instant right here, and I could get the acceleration at that instant is the slope of the velocity versus time curve. And the slope of that curve is the same everywhere. Between 0 and 4 seconds, the slope of that curve never changes. So we can draw a horizontal line. And what is the value of the acceleration? This is going to equal the change in velocity over the time interval. So the bicycle changed speed by 2.5 meters per second every second. So the acceleration was 2.5 meters per second squared. Let's think about the sign for a second. Was our speed increasing or decreasing? It was increasing. And our velocity is positive. We drew it in the positive direction. Positive 5, positive 10. If our velocity is increasing and it's positive, then our acceleration has to point in the same direction. It also has to be positive. And when we look at our slope, the slope is positive. So everything checks here. And what does the acceleration versus time curve look like beyond 4 seconds? The acceleration is 0. The slope of a horizontal line is 0. Now, real quickly, what's happening at this point at t equals 4 seconds? Can our speed change instantaneously the way I'm showing here on my velocity versus time curve? Probably not. In actuality, I would probably draw that as having just an ever so slight curvature to it right there. And then I would have a slight slope to this line. It wouldn't be exactly vertical. But for the purposes of this example, I'll just leave it as an instantaneous change in velocity, and the acceleration will abruptly change from some positive value, 2.5 meters per second squared, to 0. go ahead and sketch the position versus time curve that corresponds to this velocity versus time curve. If we know that taking derivatives is going to move down, if we take the derivative of the velocity with respect to time, we get acceleration. Well, how do we go in the opposite direction? We would have to take the antiderivative. We would have to integrate. We'd have to find the area under the curve. So when we go from velocity to acceleration, we look at the slope. And when we go from acceleration versus time to velocity versus time, we use the area under the curve. But it doesn't give us the velocity at that instant. Remember, when you integrate, you always get this constant that comes out. That constant is for fixing our initial condition. What we get is the change in velocity, delta v. So the area under acceleration versus time should give us delta v. Should we check? What do we get for the area under our acceleration versus time curve between 0 and 4 seconds? The area, it's just a rectangle. The area is just 4 seconds times 2.5 meters per second squared. The area is 10 meters per second. So delta v that's the area under the acceleration versus time curve. So that is equal to delta v. And we know we started at 0. So we have to end up at 10 meters per second velocity after 4 seconds. Now see if you can draw position versus time given this velocity versus time curve. Do we have all the information? We might all get different graphs because when we move in this direction, the area under v versus t gives displacement, gives change in position. It doesn't tell us where we're at. It tells us by how many meters we changed. So we need our initial position in order to draw this graph properly. So I'm going to tell you right now, we started at x equals negative 10 meters. So at t equals 0, we were at negative 10 meters. Well, what do we know? We know that velocity is change in position with respect to time. That means that if we're going down from position to velocity, I've drawn my graphs in a nice sequence, position, velocity, acceleration, for this very reason. The slope of our position versus time curve will give us the velocity at that instant. So we know we're at negative 10 meters at t equals 0. And we know that the slope at that instant has to be 0 because our velocity is 0 at that point. So if I come up here, I'm going to use green. The slope has to be 0. If I draw a tangent line, that green line is tangent to my x versus t curve. The tangent line, the slope at that instant, has to be 0. And an instant later, the slope is some positive small number. And a little bit later, it's a bigger positive number. And a little bit later, it's a bigger positive number. And finally, it ends up being a really big positive number. So the slope starts out small, and it becomes larger and larger, but it's always positive. So the slope is going to be At 1 second, the slope is going to be positive and small, and then it's going to be a little bit bigger, and eventually it's going to be a very large positive number 10. So our graph in this segment between 0 and 4 seconds is concave up. Now let's figure out where we are. What is the value of x at 4 seconds so we can draw this properly and not just have a rough sketch like this? Well, we're going to use the fact that the area under our velocity versus time curve is the change in position. The area under our velocity versus time curve is just 1/2 the base times the height. So we get 2 times 10, 20 meters, positive 20 meters. We started out at 0 and we ended up in the positive direction by 20 meters. So where are we? Well, we started at -10. So we have to be at positive 10 at the end of 4 seconds. And it's concave up. The slope starts out at 0 and it's concave up, and it would look something like that. And where is our object at the end of 7 seconds? If we coasted for 3 seconds, where is our object at t equals 7 seconds? Well, we take the area under this segment and we get 10 times 3, or 30 meters. So we're 30 meters, positive 30 meters from where we were at t equals 4 seconds. And we were at 10. So we have to be at 40 meters. And what does the line look like that connects those 2 points? That's a straight line. I didn't draw it very well here. It should transition, at this point, it should transition very smoothly from one curve to the other. But that's about as good as I can do drawing freehand. All right, so that was a good exercise. What I'd like you to do now, just to make sure you've got it all straight, is I'll give you what happens over the next 2 seconds. Over the next 2 seconds, you hit the brakes on your bicycle and slow down to a complete stop. So at t equals 7, you hit the brakes and you slow with constant acceleration until you come to a stop at t equals 9 seconds.